And welcome to our 9th meeting, Roundtable Workshop. I still like to count them. Our meeting will have the similar format to the others. And so, but before we get started, let me hand things over to John.
Oh, thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. And yes, indeed, Dave, Roundtable meeting number 9, and I think total Ivan meetings, Ivan Zoom meetings at this point, I think we're on number 17 or 18. And for those of you who joined our pre-ENC meeting a week ago this past Sunday, I'll dare say now famous Ivan Live from Asilomar. If I do say we had quite a spectacular meeting, and I wanted to point out, which by the way is now on the Ivan YouTube channel, along with all of the other, or most of the other meetings that we do. Videos typically come up a couple of days after the fact. But one of the really spectacular highlights of the Ivan Live from Asilomar meeting, of course, was the brand new Ivan Founders Award that started up this year and will be an annual award from here on in. And very proud to say once again that our first year's winner was Ken Sharp-Knott of Virginia Tech University. And we'll be looking for nominations for next year's award, probably about 3 months in advance of ENC. So please do keep that in mind. And but in any case, MR Resources and Q1 Instruments are very, very happy to bring these meetings to you. And we're glad you could all join us today. I'll turn it over just briefly to Don Bouchard of Q1. Don, if you could give us a few words and update, we would appreciate it.
Okay, thank you very much, John. We invite you to get to know Q1. Q1 designs and manufactures complete NMR spectrometers from 400 to 600 megahertz, and with features for routine use in the research laboratory. Want to upgrade an older system? Q1 can retrofit AS and ultrashield magnets for less than you think. Q1 offers NMR instruments with excellent performance at an unbeatable price. Q1's operating environment is Spin Studio J, and Spin Studio J has a plug-in based paradigm for extending virtually every capability, internal to the spectrometer or externally via Java-based tools for data acquisition, analysis, and connectivity. It's a multi-language platform with a hierarchical data format and global language support, exportable to third-party processing. We will soon release a new NUS plugin based on deep learning algorithm published by Shaman University and exclusively licensed by Q1. This advanced algorithm uses an iterative process of removing artifacts by a dense convolutional neural network for data consistency to speed acquisition by a factor of 5 to 10 with improved resolution. If you want to learn more about Q1 by a remote demonstration, give us a call or send us an email. Thank you.
Thank you, Don. We appreciate the remarks. Please do, folks, get in touch with Q1 Instruments. And all that said, I will now turn it over to Dave Rice to get things going for us, if you would please, Dave.
Okay, well, before I introduce Krish, I'll just go through the normal format of our meeting. There will be 3 panelists, including Krish, who will talk to about the hour, we think, except that it's Krish. And during that time, everyone should be muted and submit your questions to the chat, and the panelists will bring them up. And then after that, we'll open it up to questions and go for as long as people are interested. So with that, let's get started. And Krish, if you'd take over.
Thank you, Dave. I don't want to disappoint many of these people for waiting. They're going to listen to me for more than an hour, but no, I will try to finish it up. Before I start, I want to announce the upcoming meeting, if you may. The next Ivan Zoom meeting on research topic is on principal component analysis in NMR, and it will be led by Frank Delaglio, NIST, and University of Maryland, and panelists will be Professor Robert Powers of University of Nebraska and Professor Emmanuel Hatzakis from Ohio State. That is on the 29th April. Watch for your email for that registration. And then the next couple of upcoming meetings are one on qNMR, that is in May by Jose Napolitano, and the next one would be Pure Shift NMR by Matthias Nielsen in June. So watch out for those announcements as well. With that said, we can get started for today's discussion. So I am going to assume that you guys can see my screen. The screen before that was Ron Crouch's picture from his backyard, somewhere looking at in the space. Anyway, so I like it because I like to look in the space when I'm thinking. So I want to thank the three panelists today, David Russell, Gennady, Khirich. Both are from Genentech. Andrea Sefler, NMR consultant and a longtime friend, and she used to be in Glaxo, if you people remember her. So with that, let me get started. What I am going to talk about, yet another new paradigm. Yeah, right. Yeah, new NMR processing tool, and there is always a skepticism there. What I'm not going to talk about is, typically when I give a workshop, I do talk about this, is some amount of NMR 101 workshop, a refresher, which I'm not going to do today, because that tells you why there is yet another NMR processing tool. And I am also, in order to focus more on the application, I am not going to talk about the craft technique, implementation, the workflow, the details of that either. Instead, I'm going to focus a lot on craft 1D and examples, craft 2D and example. I don't know why that 2D is an uppercase D and the 1D is a lowercase d, but that's okay. Anyway, and then perhaps we can discuss the perspective of where this can go. And there will be a lot of things that I will not be able to talk about purely because of time frame. And Dave Rice is not too far away from me, and he has this large barge pole that he will hit my head with that if I take too long. So, but there is a paper recently came out, a feature article on craft in MRC. So you will be able to get some more information than what I will talk about today. So what is craft in a nutshell? It is, instead of a frequency domain, let me get a, I can't get that. So anyway, let me get a laser pointer. So it's a frequency domain analysis. It is a time domain analysis. What do we mean by that? Okay, so you have in the frequency domain, we go from FID to spectrum and then the table of information. In time domain analysis, we turn it around. We go from FID to table of information, and spectrum becomes optional, perhaps a visualization tool. So this essentially extract information, the 4 parameters of NMR signals: amplitude, phase, frequency, decay rate, but they are orthogonal in time domain. In other words, one has no influence on the other. And so that's the advantage of this. And baseline is one of my pet peeve. Baseline and phase corrections are a waste of time. With that, let's go to craft 1D workflow. I said I'm not going to talk about craft 1D workflow, so I'm not going to talk about craft 1D workflow. The idea is to take it from FID to table, and so spectrum becomes optional. The table is a table of offset, amplitude, decay rate, phase. In NMR language, chemical shift, amplitude, line width, phase. So we can essentially play around with how do we sort it? How do we combine these tables? How do we filter this, delete certain things? Essentially do signal suppression, if you may, search this kind of table, and so on and so forth. That's what today's focus is all going to be. So how do we go from FID to a table? We use Bayesian decimation, but it can be any decimation option that may be available. But we use, Craft uses Bayesian decimation simply because it's just there, easier for us to use. It is an iterative process. So it takes the time domain signal, which is like an FID like this. And after the first iteration, it finds a sinusoid and optimizes it. And then it does a second iteration, given the previous sinusoid as a precondition, what's the probability of finding a second sinusoid, and optimizes both simultaneously. And then it goes to a third one, fourth one, until it finds no more. The probability is very low that there is no other sinusoidal function in the residual after that 5 iteration in this particular example. So then those 5 are your peaks in that interferogram or an FID, whatever. And this is given here just to show you how that FT result will show up. And it works from because it's an iterative process and it is a probability based. Generally, it works from most abundant or most intense signal to the least intense signal. So that number represents what those signals are. And ideally, actually, it doesn't actually give you sub FIDs or sub FIDs. It actually gives you tables. So the first iteration is a table of 1 line. Second iteration would be a table of 2 lines and 3 lines and so on and so on and so forth. So even the simulation of those FIDs is not needed in principle. And simulation of spectrum at the end is certainly optional. And we can take that table and do whatever we want to do with that. So if we come back to this Craft in a nutshell, the tabular domain is represented in 4 orthogonal columns in a spreadsheet. I deliberately put the spreadsheet in quote unquote because it is a spreadsheet. You can take it up into an Excel spreadsheet and do things that you would typically do in a spreadsheet. Hide columns, hide rows, combine rows, add them, subtract them, and whatever you want to do, you could do that in here. So that's the benefit of being able to work with the table and be able to get the information that we are interested in. Yeah. So for example, a qNMR by Craft. So a purity estimation by conventional method, which would be the integral method, and versus Craft. But what is interesting is the phase correction and baseline correction. I put this slide because it's my pet peeve. Baseline correction and phase correction are ubiquitous, unchallenged prerequisites in frequency domain analysis. Whereas in time domain analysis, what is a correction? So even if we look at these numbers, 98.2%, 97.8% versus 1.0, 1:90.94, 1:0.95. This happens to be a ratio calculation. This happens to be the quantitative purity calculation. The numbers are not interesting. The devil is actually in the detail. How we get to that number is what gives the benefit of time domain analysis. So before I go into that analysis, I want to bring in one nomenclature definition here, which I call a segment, which we published that back in 2013. We defined a segment as a frequency window. All models, all time domain models are a tabular models in the Craft table, irrespective of their line width, that are within this window of frequencies are added to generate a segment amplitude. Segment window is not an integral window. There's a fundamental difference between the two. For example, here is a slide where I have an FT result, Craft result, residual model that I used to do many years ago. How well it does. But let's take, for example, that particular peak that I'm interested in quantifying that peak. In an integral, I may do an integral like that. That's not good enough. All the qNMR folks who are listening will say, oh, sorry, that's not good enough. If I take it further out, that's still not good enough, because the peaks that are right next to it is overlapping. You have to do some kind of a gymnastics if you want to get quantitative information out of that overlap region. Whereas in the segment definition, that yellow bar is considered a segment. This frequency fall within that segment. So all the models, which in this case happens to be that one model, will be included into that segment with the entire line width, if you may think of it as a line width, in its full glory. Yeah. A segment like this, which is shifted onto the side, but still that frequency fall within that segment, will still be include the entire model into that segment amplitude. We don't think about this as our line width going in, because that is in frequency domain. Time domain is just a decay rate, which is a separate column. We are not using the decay rate to sort this one out. We are using only the frequency column to sort these things out. So an interesting one would be something like that. If I have a segment like this, these two models will be included into that segment, but the model that is on the downfield side, which is very close to it, will not be included in its entirety, including all these tails that we think in terms of frequency domain. So that only those two peaks will be included. So what does it mean? Is segment allows for, I can be sloppy. I can be a little bit loose in defining where peaks are and still get the power of quantitation. Instead of sloppiness, I want to call that it gives me flexibility. Not only it gives me flexibility, it actually I can redefine qNMR resolution. So here is an example of that. Before I go further, I want to explain first what these traces are. The bottom is a FT trace. The next one is a Kraft result. All the models included in there. And these one are amplitude or actually concentration, because this is the reference concentration. Based upon the concentration and the segment amplitude, we calculate and we put those amplitude in there. And the traces are simulated traces for each one of those segments. And segments are these yellow boxes in here. Now, if you take this region out, typically they are so close to each other in typical integral definition, they will be integrated together. That's how the conventional analysis does. Whereas in Kraft, we can essentially say, that's a separate segment, this is a separate segment, that's a separate segment. I can generate amplitude of those segments. And another example would be here. This particular doublet of doublet falls right next to C13 satellite of the DMSL. And typically you would try to come up with yet another way to separate these out from the C13 satellite that is tailing up there. In Kraft, we don't have to worry about that. That is just a segment. We just make sure that the frequency, the segment is defined outside of that frequency of that C13 satellite, not necessarily the line width. So here is another example. The last example is even more interesting. For example, here is a quote unquote overlap resonances. There's a doublet and there is a broad resonance that's overlapped in the conventional definition, but they are not overlapped. As far as Kraft is concerned, they are perfectly well resolved resonances. Resolution in frequency column, they are two independent models, and we can essentially get these two models into one trace and that model into trace. A trace meaning they already know the amplitude, frequency, decay rate phase. Those are simulated traces. So in a high dynamic range scenarios, something like this ethanol example, you can actually do multiple crafting. So you can do a sequential crafting. This is the FT of the ethyl group, and these are the impurities that we are interested in. So you can do a first craft in these big peaks and take that models away. When I say away, subtract it from the original FID and submit the resultant FID into a second craft. You could in fact envision multiple crafts like this, because as I said at the beginning, craft works as from the most abundant to the least abundant signals. After the second craft, we have a full definition of all the peaks in there, and we can generate amplitude of all these signals. What I would like to show you is this C13 satellite of that thing is 98.9 to 5.55.54. So you already actually have an internal referencing, quantifiable referencing that's in there. So in other words, this allows craft, being able to do it in time domain allows you to do all these manipulations with the table, and the spectrum, as I showed you in here, is nothing more than a visualization of these results. These results of amplitude and how vertical scale I need to set in order to see it on the screen so that I can present in a conference. So that's what becomes a spectrum becomes. So I want to hand it over to Dave to talk a little bit about crowded spectrum. I call it a crowded spectrum, and he's probably going to talk to you about using that under reaction monitoring. Dave, take it away.
Thanks, Krish. Thanks, everybody, and good morning. So, as Krish says, I'm going to talk to you a little bit about spectra that are somewhat crowded. This is work we did a few years ago, but it's an interesting example of where craft is actually a valuable tool for us. Anybody that does organic chemistry understands that doing a reaction monitoring is a very valuable thing. And there are a lot of tools for doing this. NMR actually is a great tool for doing reaction monitoring for all the reasons I've got here on the screen. In our environment, we actually do this kind of two different ways. When you're running a research kind of route scouting experiment, it would be nice to understand more about what the chemistry that's taking place in your reaction is. As you move up in scale to the picture we've got here, you probably understand your reaction, but you still need a way to monitor your reactions to determine when they're going right, when they're going wrong, and if it's working. NMR is a great tool for this. It's been used for many years. The problem is a lot of that work was done with big superconducting NMR magnets, and for a lot of reasons, they're not necessarily optimal in that application. Benchtop NMR is great for this, however. They're cheap and relatively easy to operate. You can put one right in the chemistry lab. They don't take a whole lot of facility stuff. In our case, we put a flow probe on our little Magritech spin solve. So that actually is a peristaltic pump on the front, and we can pump through the NMR in real time, collecting flow data as we go. It's a great setup, but when you tell people you've moved from high field to 60 megahertz NMR, the first thing everybody says is, oh, but what about overlap? Krish kind of already alluded to the overlap problem and what it really means and why you have to be careful about what you're going to say when you talk about overlap. I'd like to take just a quick slide here and talk a little bit about the three things we really care about. Overlap, as I say, is often misused and sometimes convoluted. What people really talk about when they go to low field, what they should be talking about more than resolution or overlap, is actually dispersion. So this is the NMR spectrum, same tube, two different magnets, two different fields. What you see is your resolution at low field doesn't actually get much worse. In many cases, it might even get better. But what you lose by going to low field is dispersion. So the peaks are all the same resolution, they're all the same width. We just simply have less floor space to put them all in. So you begin to scrunch everything together. And that's why when you go to 60 megahertz or any other low field system, we would have to take all of these peaks that we see and scrunch them into a window about that wide. So in the frequency space, they are absolutely going to be overlapped. But in the time domain, that's actually not true. As Krish points out, in the time domain, as long as you've got acquisition time and long enough to resolve the difference in frequency between two peaks, they're not overlapped and craft can pull it out. So craft seems like the perfect application for processing data on our flow system. So we ran this model experiment to collect some data we could talk about. It assembled 3 alcohols doing an esterification. And this is what you get. It really doesn't look that bad. We collected data for about 30 minutes, a spectrum every 30 seconds or so. And what we were looking for were changes in the spectra over the time course as we monitor how the reaction goes forward. I'd like to draw your attention to this peak. Those are actually the aromatic protons from the benzyl alcohol. If we expand that up a little bit, you can see that as over the course of the reaction from beginning to end, a new peak does actually grow in there. And because your eyeball can pick that out, they are resolved. In the frequency space, the peaks are overlapped, but the frequencies themselves are clearly resolved. The problem is using a typical method, some kind of integration, hopeless. As Krish says, it would just be hopeless. Now, this is not the data itself. This is actually reconstructed from the craft table. In the craft world, those frequencies are completely separate. They're in 2 different segments. And all you have to do is go into the craft table, pull them out, measure the amplitudes, and you've completely resolved those two peaks of the benzyl alcohol. Now, I only put Spectra like this up because a lot of people like to see the spectra. People always worry about the pictures. But in reality, what the process chemists want are just the numbers. They want to be able to plot the numbers, measure rate constants for the reaction, how it's running. They want to know if the reaction slowed down or stopped or not, how it's working. So this is what we're really after. And don't ever lose that idea. I mean, a lot of the work we're talking about, a lot of the stuff Krish is talking about, it's really not about the spectra. It's about generating useful information, reducing the spectra to something we can use in our real world. Now, this is a much worse case. If you look at the two peaks here, that little singlet is actually the methyl groups from the neopentyl alcohol. It's in a very crowded region of the spectrum. And I would argue that anybody who's trying to do reaction monitoring on that would really struggle if you're going to pull that out from the frequency space. It's just not going to work for you. But Kraft doesn't care. Again, we haven't lost resolution. We've lost dispersion. The resolution is still there. You pick the correct segments. You can pull out the peaks that you want. And from those, you can generate these types of data. Now, this was very interesting to us, actually, and it just speaks to the power of this. I had no idea going into this how it was going to turn out, but I plotted these data and said, yeah, that looks pretty good. And then I went and talked to one of the people here at Genentech who did a lot of kinetics work. And he said, you know, we can model that very easily. Because you've got reactant going to product, the two sets of data are actually coupled. So at the beginning of the reaction where your reactant concentration is high, you can get the data with very high resolution. As you can see, the ester product is very low concentration at the beginning. When there's no signal to noise, there's nothing you can do. But as it grows in, you can use that instead of your alcohol if the alcohol had decayed all the way to zero. Obviously, this reaction didn't run to completion. And you can still generate reaction constants from that. In this case, we found that this was a two-step reaction. You couldn't fit it with one single reaction constant, rate constant. You actually had to have two. They're different by just less than an order of magnitude. This is exactly the kind of information that the chemists would like to have. How fast is my reaction running? What's the slow step going to be? And how can I change that to better understand the reaction and do a better job with the chemistry that we're doing? This was a great project. It was actually a lot of fun. A number of people I would like to thank. In particular, I've got to call out Brianna Conklin. She did most of the work to put this thing together and collect all the data for us. Krish, Kraft, saved us. We loved it. Thank you. And I will give it back to you.
Thank you. Okay, so with that, I also want to go to the next item in thinking about NMR analysis is, I didn't go into the phase correction at all, and then except that I just called it it's a waste of time simply because phase is just yet another parameter as in a completely orthogonal column in the table. So there is really nothing to correct. It's just phase is phase of a particular signal. Baseline is yet another ubiquitous step in all conventional processing. But baseline distortion, whatever may be the source, we are not going to talk about the source, is nothing but a distortion of early points on the time domain. This slide is courtesy of Frank, and I have the tendency to steal a lot of his slides. So this is one of those stolen slides. So distortion of localized early points in time domain, eventually when you do a Fourier transform, it gets into baseline distortion that extends over all point. But we can take that one step further and then think of broad peak and sharp peaks as broad peaks decay very fast, and so they dominate the early point of the time domain. Sharp peaks decay slow, and they dominate the later point of the time domain. So you can imagine really broad signal essentially spreading across your entire frequency domain simply because we just did a Fourier transform of the entire FID. What if we take this Kraft workflow, instead of hide, sort, combine, filter, we simply say, okay, I'm not interested in any model that are wider than, say, 5 Hertz. I consider 5 Hertz to be my narrow lines, and anything beyond 5 Hertz to be broad resonances. All I'm doing is taking the table and look at the decay rate column, and then simply say, hide anything that is less than 1 over pi times 5. So you can do that. Here is an example. where this is actually a spectrum of, the black line is a spectrum of a blood serum spiked with known small molecules in there. This is a very old spectra that we had. So you can essentially cast phi, meaning anything, craft assisted spectrum sorting of 5 Hertz models. So these are all 5 Hertz models inside that, and then the residual would be subtracting the sum of all these 5 Hertz models from 5 Hertz or below models from the original FID and Fourier transforming the FID to generate the residual. So if you want to look at and expand this particular region, for example, this region is expanded, and you can see that every one of those peaks is very well resolved out and quantified, if you may. Characterized is a better word from that spectrum, without worrying about the background that's in there. Yet another more complex region would be this. For example, in here, these peaks are this doublet. There's a doublet there. There's a doublet that's riding on top of the this peak at 1.3, and so on and so forth. There are several sharp resonances. We know that these are because these are spiked sample. So, but no ultrafiltration needed, no CPNG, which is one of the most common NMR experiment that we tend to do in order to get rid of all these broad resonances so we can analyze the sharp resonances. This is just a pulse acquired experiment, and we can generate these kind of very good quantifiable, characterizable tables and do whatever qNMR analysis that we might do with them. With that, I'm going to pass it from again. I'm going to do another pass to Gennady on broad peak and sharp peaks, and Gennady, take it away.
Okay, thank you, Krish. Okay, great. So I have a short presentation to show everyone just regarding some of the uses of craft here at Genentech. So Genentech, here at Genentech, we're a biopharmaceutical company. You know, we're in the business of making antibodies, and I work for the small molecule process impurities group. And so our job is to hunt for trace small molecule impurities that are usually buried in a sea of protein and excipients. So you can very loosely think of the biopharmaceutical manufacturing process as being divided into 4 stages, at least from a naive NMR spectroscopist point of view. We can start with cell culture and harvest, where you have a complex mixture of media components, metabolites, and other additives. Then there's a bunch of purification and chromatography steps. And so we're looking at the clearance of upstream raw materials used in cell culture. Sometimes we look at the resin performance and if the chromatography columns are leaching anything into our process pools. Then there's the ultrafiltration diafiltration step, also known as the UFDF pool. So this is post-chromatography. So this is a highly purified, highly concentrated protein solution. And it's not uncommon for the protein concentration in these solutions to be anywhere from 50 to 200 milligrams per mil, which, at the high end, that's about 20% protein by weight. And a lot of times we'll look at filter leachables and, additional clearance of upstream raw materials in these process pools. Finally, we have fully formulated drug substance and drug product. And this becomes complicated because now, unlike the UFDF pool, which is, a very simple buffer solution with protein, now you have a bunch of additives, also known as excipients. A lot of times polymers, sugar, and these are all present at very high concentrations. So these make for very crowded spectra and require extremely high dynamic range capabilities. And so a lot of times in solutions like this, we're going to be interested in excipient-related impurities, leachables from container closures such as vials, syringes, and stoppers, or even leachables from single-use technologies such as storage bags and filling assemblies, especially since some of these single-use technologies are actually gamma irradiated for sterilization before use. And this is kind of where the industry is going. So this presents unique analytical challenges. And so traditionally, our workhorse approach involves suppressing the antibody signal with the use of a CAR per cell Meiboom gill relaxation filter, also known as a CPMG. And we typically use direct external standards for quantification, right? So it's always an apples to apples comparison. And so here's an example of the same exact sample without a CPMG on the left and with a CPMG on the right. So if you look at the spectrum on the left, you basically see monoclonal antibody or MAB signal everywhere. You see a little citrate buffer popping up. If you look really hard, you might see some small molecule peaks kind of, popping out of that CF protein. But once you turn that CPMG on, with a good 200 milliseconds or so, all that antibody signal just, goes away. You get this beautiful flat baseline, and you can start to see some of the small molecule impurities in there, such as tris, acetate, and propylene glycol. There's also some isopropyl alcohol in there, which I haven't labeled. What's interesting is that the CPMG is not actually needed when it comes to craft. So as Krish mentioned in his previous slide, you can just filter out all resonances that are broader than a certain decay rate, simply by putting in a Boolean argument into craft. And so what you're seeing right now is actually the same exact spectrum. The same sample, the different spectrum, but this was actually collected without a CPMG. And what you're looking at are spikes of MES buffer, acetate, tris, and propylene glycol that we added in there. And so craft is just the table of numbers. So what I'm showing you is just a pretty picture, right? The real data is actually in the craft table. So no integration needed. You just look at the craft amplitude. Now the UFDF pool, as you can see in the CPMG spectrum, that's a pretty clean spectrum. It gets a lot more interesting when you talk about fully formulated drug substance. So here's an example of a fully formulated drug substance where you have a ton of sugar, and there's also a ton of histidine buffer in there, and there's all that protein signal. And again, we spiked in tris, propylene glycol, and acetate, and craft can pick these out no problem. Of course, the most impressive one is tris, because that's buried in a sea of sugar. And there's absolutely no way of accurately quantifying this, even with the use of a CPMG. And just to show you what the performance of traditional integration versus craft is, here are the three analytes: propylene glycol, acetate, and tris. And in each of these plots, we have an integration of that analyte versus the craft amplitude plotted against the actual target spike, the target concentration. And we have it in proteinless buffer in the UFDF pool. So the difference between these two columns is no protein. And then we also have it in formulation buffer without protein versus fully formulated drug substance. And as you can see, there is no meaningful difference between integration results and craft. And the most interesting thing here is going back to tris and the fully formulated drug substance. As you can see, there is no or rather, there are no integration results, only the craft results, because there's no way of actually getting at this with tris. And so another common example that of some of the work we do is sometimes our cell culture colleagues, they give us some cell culture material, some harvest cell culture fluid, and there's a polymer that they actually spike in there as an antiviral agent known as Triton CG110. And they spike it in at 0.5%. And they, after mixing, they give us a sample and they ask us, can you verify that we put in the correct amount? Now, the spectrum of Triton CG110 all by itself, not a problem. But when it's in harvested cell culture fluid, as you can see, this is a nightmare. And typically what we do is we actually run a series of HSQCs on this. And as you can see with the integration, the HSQC is perfectly linear, and we can get them the answer that they need. We can also run 2D craft, and as you can see from the plot on the bottom right, again, there is no meaningful difference between integration and craft. But given the capabilities of craft, it does raise the question: why run a bunch of 2D HSQCs? Because on second thought, we can just run this as a 1D now. And you get perfectly linear and quantitative results. So craft really does open up a whole new world of possibilities in terms of what we can get from a qNMR point of view experimentally, and also with simplifying the workflow. So on that note, I just want to acknowledge Ken Skidmore, Noah Wake, Dave Russell, and of course, Krish and Dan for all the help with crafting our collaborations. Thank you.
Thanks, Gennady. Let me take over. Okay, so I'm going to spend a very little time on this one, but we can take it up in the discussion just so that I don't run out of too much of my time. So when you are doing, this is an example of omics NMR. This is actually cell culture data. This is the FT results. There are 4 colors. They are drug treated. I think there are 1, 2, 3, 4. Yeah, 3 of them are drug treated. One is a vehicle, and then you have, this is the craft result, untargeted 2 Hz segments across the board. 2 Hz segments. We just, wherever there are peaks, we set 2 Hz segments and put it in principal component analysis. They separate out, and you can do that in a targeted quantification, custom segments as well, and generate your spreadsheet based bar chart. The idea is spectral visualization itself is optional. Simulation is optional. Spectral representation is an optional. What do I mean by that? Let's take the workflow of crafting a whole bunch of related samples in omics NMR or food sciences. We supply a bunch of FIDs to craft table. If I haven't convinced you yet about the baseline correction, phase correction, and all that, that's all needed. Not needed. They are not needed. You just have a bunch of craft tables, a whole set of craft tables, and you do a segmentation of that with 2 Hz segments. Essentially, it just looks for the most dominant signal to the least dominant. It picks a dominant amplitude and then say 2 Hz segment out of that, and then take that away, and then go to the next dominant 2 Hz segment out of that, take it away, and so on, so forth. It's just an iterative process, purely computational, and you can do generate untargeted segment tables. And you can do your principal component analysis, and then potentially, I'm not a metabolomics guy, but or not a PCA guy, but I'm just saying that from PCA you get statistically some significant segments, and loading plot, whatever the PCA jargon that you're going to learn next time. You can generate a targeted segment out of it that is statistically significant segments, and then you can use the craft table to generate spectral visualization. That's optional, but you can spectral visualization. And as a user, I would like to quantify I would like to identify what it is and what that segments are, so that it tells me what that drug is doing. So up until this point, there is no user interaction. So there is a potential opportunity to do automated workflow in omics all the way from FID to statistically significant segments and generate the targeted segments from the same craft table. This whole thing has no need for operator interaction. That's a potential opportunity that exists. I'm going to segue out of 1D to 2D NMR. So in a conventional 2D NMR spectroscopy, we have 64, this is 64 increment. I think this is 101, 11024 increment or whatever, something like that. You can see that visually. I should have put the numbers in there. I didn't. But if you do an FT, you get this broad peaks and you get this small sharp peaks. So you increase T1 max. So we say when we do 64 increment, we get a spectra like this. You get 128 increment, you get a spectra like this. And 1024 increment, you get very sharp resonances, but at the expense of 1 hour and 44 minutes of time compared to 6.5 minutes of time. So increasing the number of increments is what we are target after, which we do it nowadays with significant new advances, non-uniform sampling, aliasing. There are hundreds of different tools that people do. Linear prediction, for example, is yet another. But this is the incongruence here. Why do we need to increase the number of increments in order to generate sharp resonances? The line width is should be dominated by a decay rate, which is independent of how many points that we collected. It should not how many. What is the T1 max rather? because it's how long you collect has nothing to do with what is the rate at which it is decaying. So that's the incongruence in this kind of an approach. So the problem here is typically, invariably, in all our processing, we do zero fill, we do apodization. It is the zero fill matched window functions and with Fourier transform is what causes this line width increase. And so, and Craft does not require any such apodization, and so you can get much sharper resonance out of that. Again, I am not going to go into the workflow. It's all described in the paper. If you want to discuss further, or we can discuss during the discussion period today. So if you take the time domain interferogram, these are all more or less automated. You just directly gets a tabular domain cross peaks, and that cross peaks can be visualized in spectral domain. So it's becoming it is turning the whole thing upside down. We are going from interferogram to cross peaks, and then from cross peaks we go to spectrum, and spectrum becomes optional. How do we do that to some extent? Here is an interferogram, for example. This interferogram, when you do a Bayesian analysis, it says I can fit this into 6 different models, 6 models. If I add them all together, I get that interferogram. You can add them together, and then you can actually see the Craft result. And the difference between the two is this orange line. That's the residual. And you can do a conventional Fourier transform with zero fill and apodization, and you get these six signals in there, which is actually, these are actually doublets in there. But there is nothing that is stopping me from this table. There's nothing that is stopping me saying that don't synthesize an interferogram and stop at this 64 increments. Synthesize as much as you want. It's almost equivalent to saying linear predict. And so if I can linear predict in the individual components in there, and then I can transform that, and I can actually get the doublet, and this is actually a doublet with this input FID or input interferogram. That's where it comes in. So I just made a statement about it's a linear prediction. I just wanted to show you a comparison of the conventional linear prediction versus what we do. So if this is a doublet, two doublets pairs, and the coupling constant is 16 Hertz. This happens to be a general coupling. It's a pretty strong coupling, 16 Hertz. So 1 over JHH is 62.5. So we say you need to have an interferogram 62.5 in order to resolve those peaks and so on and so forth. So in 150 increments, your T1 max, actually this is T1 max, not 1 over T1 max. Your T1 max is 33.6. For 256, your T1 max is 57.3, and still not quite there. So when you just do a regular FT or a FT with apodization, you don't, I think these are just FTs, you don't see a resolution. But if you do the conventional things that we do all the time, in fact, we do it without even thinking about it, in most of the automated processing is some kind of a linear prediction. 4 times linear prediction, voila, we can get those 2 doublets resolved, even though we collected only 256 points. But if I take this 150 increment data and do Craft, I get those 2 guys resolved in the conventional definition of resolution almost to the baseline. It's almost like a 1024 or 2048 increment interferogram. So there is really no reason for me to demonstrate to you 256 will also give you the same kind of result. Game, set, match with 150 is good enough. In the point being, in 150 points, it is a Bayesian-based approach of fitting that to exponential decay model, the best combination of exponential decay models that are being fit, and it says that I can fit that with 4 instead of just 2. And that's how you get this kind of results. Craft 2D is very generic. We have demonstrated this with a variety of 2Ds, not only in the paper that we just published this year, but also in the previous papers, 2D and non-uniform sample papers. And so I'm not going to go into that details, but the point that I wanted to make was it is from interferogram directly into your cross-peak. With that, what I want to say is a spectrum, I keep saying, spectrum is actually a representation of that table. It is not the table is not a derivative of the spectrum. So spectrum itself becomes actually optional. And with that statement of spectrum itself is optional, I want to hand over to Andrea to say something about what she thinks about spectrum versus table. Take it away, Andrea.
Okay, thanks, Krish. Okay, so thanks, Krish. So as my title of consultant implies, I no longer do NMR in the real world. So my role here is kind of to propose a series of thought experiments to kind of get the juices flowing of what we might be able to do, particularly with 2D craft. So as a framework for this thought experiment, I want to go back to some things that Krish and Dave Russell have brought. And this is that concept of thinking about NMR in terms of information and what information's in it, not spectra. So I have here a little quote here from the father of information theory, Claude Shannon, that's very NMR centric here with the use of his terminology about resolution. So let's see, I guess I got to turn off the drawing too. Okay. Okay, so what do I mean by that? So if we think about a 2D NMR FID, the information that's in there are the frequencies, the correlations between those frequencies, the amplitude, which is effectively the integration. We've got phase, particularly if we're talking about multiplicity edited experiments, there's information there. And then there's the decay rate, which Chris just kind of alluded to. What we're really trying to get around that, right? The problem with the FID is it's really mostly opaque to human interpretation. So really the sole purpose of the Fourier transform is we're turning that information into a human readable format, or the spectrum. And that's great, but the problem is that we've taken all these disparate pieces of information, these pixels, if you will, and created a picture, a single picture out of all those pixels of information. And in doing so, we have a single object now that we're working with. And the human eye we're very good at reading pictures, and that's great, but we miss details. The human eye misses details, and we're looking at a summary of the information. So what craft is really doing is it's working with the raw data, it's extracting the information directly from the FID, and then presenting that visual representation for the human eye to do. But we still have all of those pixels, all of that information deconvoluted and intact. So the question is that now that's the case, let's start thinking about some creative things we might be able to do with that information. So here's a simple example. Back in my day, carbon, chemists really liked their carbon 1Ds. That's great. They may not be, that may still be true, I don't know, but maybe it's just they're not as used to looking at 2Ds as we are. And what we can do though, the problem with them is they're very expensive to run in terms of instrument time. But you can get, for instance, an HSQC multiplicity edited in about, what, 5 minutes? If you wanted to get sort of the equivalent information in a carbon spectra, that would be a depth 135. That's going to take a lot longer. So one thought here is we can still get that information out of the multiplicity edited HSQC, but we can present that information to the chemist in a depth 135 format. So if that's fine, if the chemist is more comfortable looking at the information in that display, why not give that to them? So if they ask for the depth of 135, run the HSQC, and then show that information to them in the way they are more used to consuming it. So one objection you might have, and it's a very good one to that, is, well, wait a minute, that's stupid. We've just thrown away all of the proton information. Why would you do that? So that begs the question is, okay, all right, well, let's preserve that information. Maybe there is a way that we can still present this information in, for instance, a 1D format that a chemist might be more comfortable with. and this is just a simple example. You take their proton spectra. I'm a terrible artist. Maybe you can do this more visually appealing, but just take their proton spectra, take that synthetic DEP-135 experiment, and simply draw lines between, okay, that proton belongs to that carbon. Maybe there's a better, prettier way to do this, but now that we just have the information and we're simply displaying the information, we can begin to think about better ways to do that. This is another example. This is something that I worked on a number of years ago. This was a terpenoid that I had a couple of micrograms isolated out of plasma. So these are really crappy spectra. On the left there is the Fourier transform spectra, and I just simply could not assign definitively some of these cross peaks here because of the overlap. So gave it to Krish, he crafted it, and that was great. So now I can assign which cross peak belongs to which diagonal. But Krish kind of said, well, there's really no information in the diagonal. You're not getting any additional information. It's really just getting in your way. So let's just remove it. We can tell from the craft table, they'll have the same frequencies. So let's just get rid of that, get it out of the way, and get straight to the information we really want to see. So not only can you emphasize the information you want, you can get rid of the stuff that's actually in your way that's not giving you additional information. Along the same lines, this is something we often deal with in mixture analysis. We've got something large, and what we're really interested in is the small impurity. So we can start thinking about, well, okay, I don't want to see this big thing. I know what that thing, what I really want to do is see what the smallest 25% of the peaks. And we can do that from the craft table, is just take the smallest 25% of the amplitudes and show the subspectra of that. We can get even funkier with that, right? So maybe you've got a whole bunch of schmutz in the baseline. So maybe now what you want to see is actually the middle quartile of your peaks. So you can do that. Another thing that's even more creative is if you know, okay, I know this peak is from the component of interest. I want to show things that the amplitude is maybe plus or minus X% from that. So now we're starting to think about just isolating. I think these are all from these signals are all from the same component in that mixture. Here's another example of thinking about the information. So in this case, we've got a diagonal of a multiplet that's really ugly. It would be ugly in the 1D as well. It'd be a very complex multiplet. But if, particularly like in a DQF cozy, the cross peak is going to have much more simplified coupling information, because we're only going to be looking at the coupling information between these two components. So rather than going to this ugly multiplet and analyzing the coupling from there, let's grab the coupling information from the much simplified cross peaks and use that to do our multiplet analysis. If we can do that, now we might be able to think of, okay, if I can really reliably and predictably understand that coupling information, now I understand where the center of that multiplet is. I understand the coupling. I can computationally go back to this diagonal peak or the 1D and computationally decouple it rather than running an experiment to decouple. So this gets to the concept of pure shift, which is a wonderful experiment if you work with complex mixtures, right? To collapse all of this hideous multiplets into simplified singlets. But for any of those of you who have ever run it, it's a terrible experiment. The sensitivity is awful. So if you could do this computationally, that would be very advantageous. So here's an even crazier thought. So if you can reliably collapse your multiplets into singlets, if you think about the amplitude, if you normalize the amplitude of the smallest signal from a component to 1, every other component, every other signal from that molecule or that component should have an integer relationship in amplitude to that smallest component. So it should be, right, 1x, 2x, 3x, or if you got a tert-butyl group, it's going to be 9x, something like that, but it's going to be an integer relationship. So if you could think about an algorithm that would go to your smallest peak, set the amplitude to 1, and now go find me everything in my spectra that has an integer relationship to that smallest amplitude, and put that in one bucket. And now move on to the second smallest. Set that to 1, and then go out. So I'm going to throw out everything that's 2.5 or 3.7x. And that might be a way to start thinking about intelligently bucketing a mixture into signals that we think belong to a single component. So now if we have a suite of experiments, okay, so if you think about a 2D experiment, that is another thing that cross-peak tells you, is if you have a cross-peak between two things, that's telling you that those two signals belong to the same component. So we might be able to start thinking about, again, going to a mixture spectra and creating some algorithms that might intelligently start separating all of our signals into things that we believe belong to the same component. And if we have all of the information in tables, it becomes much easier to do that. So what I'm talking about here is essentially computational chromatography. Can we do that? Can we do that intelligent sorting? So I'm gonna stop there. Those are some crazy thoughts. What I'm really talking about, so this is a woman who was very influential in my career. She always proposed the question, what are you going to do with the information once you have it? And that's really what we're talking about here. We've created NMR information into these separate components, and now what are we going to do with that information? We could show it as a spectra, but there's a lot more creative things and interesting things that we can do. So I'm going to turn it back to Krish to get back down into the details and reality.
Okay.
Okay.
Thanks. You have to, okay, you got it. I know we are running already behind, and I know Dave Rice is smiling, and he told me that I'm going to be way out of my time. But I will try to cut it short a little bit, and then perhaps take it up into discussions. But I will finish it off with one topic on, that will just follow what Andrea was talking about. And I said Craft 2D is generic, obviously, for pretty much a whole host of experiments that we have published examples of. So it gives you from interferogram, which is a 64 increment complex, that is 2 times 64 number of FIDs that we collected, to cross peaks, and cross peaks are represented in a table, but in that table, we essentially present them in 1024 complex points rather than 64 complex points, 64 and then doing apodization, zero filling. We just don't do zero fill. We simply say just compute it to 1024 complex. But 1024 complex is just arbitrary, that we think that, oh, we are going to Fourier number in this dimension, I'm going to keep it to 2048 or 2K. That's completely arbitrary. There's nothing that is stopping me from taking that, and then for every one of those cross peaks, I simply say, okay, show me a 1D type spectrum, because for each cross peak, I have all the information, all the models that contribute to that, all their frequency, decay rate, phase, amplitude, everything that is in there. Just compute them into 32K complex point, but then present them each line as a single line with the phase up or down. And so this becomes a selective, Andrea was just alluding to this, is a selective depth experiment, if you may, depth spectrum, if you may. You can do that, or you can do as was pointed out, we can simply do add them all together into a single depth type experiment, 32K complex synthesis and transform, and you can actually see these two cross peaks that are 2 ppm apart, about 0.2 ppm apart in carbon, pretty well separated out in your carbon, quote unquote carbon spectrum. Now, I just want to take one item, which is, I hope to do that in 5 minutes, is spectrum is a representation of the table. So we can actually use the table to do all kinds of stuff with that we don't, without looking at the spectrum at all. If you have a reference material, for example, 20 millimolar mestranol, I can look at the table in a different fashion instead of the cross peaks, I simply look at this as fingerprint. Fingerprint includes F1 frequency, F2 frequency, F1 box being the uncertainty within that within this chemical shift. This is the uncertainty, or actually the the width of your proton, meaning doublet and triplet will have a wider width in that dimension, and so on and so forth. So you can essentially look at it as a fingerprint. This came out of the Kraft table, and it also has an amplitude. So I can show you the fingerprint in an example like this. The lighter ones are FT results. The darker ones are Kraft in the conventional way of displaying, and the green ones are the fingerprint boxes overlaid on top of that as a box representation. So once you have this fingerprint, I can take an unknown. In this particular case, I have a mastronol of unknown concentration. I simply generate a Kraft table that has only F1, F2 ppm and an amplitude. And I have the reference fingerprint, which is 20 millimolar. I can plot this amplitude against that amplitude, generate my concentration out of that without looking at the spectrum ever. And I can do that in a mixture. This happens to be a mixture of mastronol with an impurity, and that's Kraft 2D table. It's a long table. It includes mastronol and everything. I can simply use the fingerprint not only to just plot against each other, but also just search this F1 and F2 in this table and take those amplitude, plot that amplitude against each other, and generate a quantitative result from the slope. Alternatively, I can take that sub table, which is this table that is just the peaks that are mastronol, and generate a mastronol spectrum. Or I can subtract the mastronol table out of the first table and generate an impurity spectrum. So it gives you a lot of flexibility of playing around with the table without needing to do anything in the spectrum. So we actually did non-uniform, a whole variety of concentrations, impurity based, number of increments, less number of increments, more number of increments, number of scans per increment, non-uniform sampling, 50%, 38%, and a whole bunch of those. And this table is boring. You can actually just plot them. All the correlations are somewhere in the order of 999. You are plotting every peak. Every peak is important. I have a reference material. I plot it against something else. Now take it to one step further into depth lookalike. This is a 20 millimolar strychnine. That's a depth lookalike spectrum that we talked about. Now I want to take it a little bit further. What if I have an ASAP HMQC spectrum? This is an ASAP HMQC spectrum. FT is these open circles, and Kraft results are these closed red circles. And then I can say, oh, I can get the carbon spectrum in about a minute of acquisition, 1 minute of processing. And then I say, yeah, that's fantastic. I compare that to carbon observed spectrum. That's a 1 hour acquisition. Yeah, it takes only less than a second to process, but it does take some less time to process. But the point is, this whole thing is in a table. All this thing that I showed you behind are optional. We have 2D connectivity, that's a bonus. But what is more interesting here is I have an F1 chemical shift against the amplitude. Now, if I want to do some kind of a time course monitoring that Dave Russell was talking about earlier, but using carbon positions on a 1 minute acquisition with 1 minute processing. So essentially, my time course can be 1 minute data point, 1 minute time course points. I can monitor this 60.26, its own amplitude against 60.08 with its own amplitude. And I actually do a time course monitoring of these things. There's a potential opportunities that exist simply because we deal with tables rather than take the table, try to extract the table from the spectrum. Now here is a benchtop NMR spectrum. I'm going to do a little bit faster here. This is the FT results. FT results 64 increment, 128 increment. Kraft results pretty much 64 and 128, pretty much exactly the same. In fact, you can actually say what is the value of this by plotting the amplitude of the 64 against the amplitude of the 128. That's with a slope of 1 with a correlation coefficient of 99, because amplitude is the first point. in a sinusoidal decaying sinusoid. And that is the same whether it is 64 increment or 128 increment. I also did that with conventional height experiment. I did deliberately made it not useful. That's just a silly thing that I tend to do. But what's the price to pay? There's no free lunch. What's the price that we paid by going from 128 to 64? The price you pay is the uncertainty in these positions. Positions or amplitudes are displayed in this plot. Uncertainty in the amplitude, difference in the amplitude. Positional also, that's 0.07 ppm uncertainty average. This is 0.15 ppm, but let's just compare it with spectral with over NI. This is 2 ppm, that's 4 ppm. Yeah, I agree, this is not a fair comparison, but some kind of a comparison. The point being that we can do lots of things by simply doing computationally, crafting them and generating the table. So it begs a lot of questions. Is there any benefit to run a greater number of increments, which is, you can throw your hands up and then say, this after a certain minimum between, makes no sense, no reason to, unless you have two cross peaks in the same F2 trace and you want to resolve them like a doublet. Should one run more scans per increment with a lower concentration? Perhaps in benchtop. Venture into complex samples at low field. We get into qNMR of mixtures. Omics classification by benchtop NMR. What's wrong with that? We can resolve it pretty effectively. How about benchtop, ASAP, HMQC, and CRAFT-2D or ASAP depth experiment to monitor reactions with C13 amplitude? These are, I don't have examples to show you, but I just want to kindle interest in that. With that, I'm just going to jump. There are a whole bunch of 4 or 5 different slides that I want to talk about, but I'm going to jump straight to the last slide. There are miles to go. I am not saying that I have done everything that can be done. There's lots of questions. I'm hoping there's lots of questions. CRAFT-2D of Crowder spectrum, bio-NMR, CRAFT-2D in benchtop, NMR 1D or 2D. I never talked about MISTA, but I talked about MISTA in the Ivan meeting at Live from SLOMR. I never talked about aroma, but it is something very similar to what Andrea was talking about in using the quantitative numbers and relative amplitudes as a guide, amplitude ratio, aided overlapping multiplet or mixture analysis. I never talked about combinatorial 2D. ISOs is something I never talked about. This is in silico oversampling. Perhaps we did that for 2D. We can do that for 1D for broad resonances like polymers. Automation, faster. With that, I want to thank the lot of collaborators, lot of innumerable gurus, lot of critics that what made this so far going. And I actually want to thank the 3 panelists who are willing to put up with me. And I leave this screen on the leave this slide on the screen until somebody wants me to unshare it. Leave it up to discussion at this point. Any questions and any chat? That I can't see it when I am putting it in a screen share mode. So I'm going to assume my colleagues will look at the chat and tell me what, or you can I will give it to Dave and let Dave explain how things go from there.
Oh, okay. Well, I think at this point, perhaps the panelists who have been looking at the chat might bring up some of the questions from the chat. And I think at this point too, anyone from the audience should unmute themselves and bring up questions directly to all of us.
Okay, so I've been keeping track of some of the questions, so I'm just going to start in chronological order. So from Ricardo, we have 2 questions. The first question was, could you test different combinations of those single quote unquote convoluted peaks from a complex mixture to match database compounds?
Yes, it is potentially possible. The Bayesian package that we use is from Larry Bretholz from Washington University. We are simply using only the single exponential decay model as our input model, and it is fitting to, in an iterative fashion, it is fitting to. But if you have a complex model, for example, a simple thing would be like a quartet. If you know the J values and the chemical shift, not the chemical shift, the J value and the ratio of these things, you can supply that model, which is a complex model, if any, not a single exponential decay model, a complex exponential decay model, and then say, find the probability of finding this model in the complex mixture, and it will do that as well. Alternatively, what we are trying to do post crafting using single exponential is using the amplitude ratio. This is where the aroma comes in. You can actually use the amplitude ratio to extract groups of, if you make groups of exponential models out of the table. The table is pure exponential models, a whole bunch of them, and then we look for this group of exponential models. In the aroma, we actually say where at, rather instead of going at probability of finding it in the entire table, we simply say around in this place, get me a quartet which has this 1:3:3:1 ratio. And actually aroma I developed it for much more complex multiplet. I could not show a result simply because I didn't ask permission to show that from a collaborator. So until then I can't show you, but essentially the idea is you have a pattern that you have from your known compound or known standard, and that pattern of amplitude ratio and the frequency positions is now used to subtract out that pattern out of an unknown in that area of spectrum, and then you can analyze the residual for anything that is buried under. That's the idea. So yes, multiple different things can be asked to use. We use a basis set of always all of them are exponential models. We just use that because that's the easier one. I'm not a mathematician, nor I claim to be a software person. I just look for the easy way around, and the exponential model seems to be an easy way around for me. So that's what I use. But yes, the Bayesian package does have a whole bunch of stuff. Any model that you have, that's what the Bayesian, if you look in the documentation there, any model, as long as you can mathematically define that model, you can approach a similar iterative process. I don't know if I answered the question, but.
And then the second question from Ricardo is, are these, again, quote unquote, deconvoluted peaks quantitative? I think I could answer that. Of course, it's quantitative. Yeah. Everything does is quantitative. But going back to the database, to database matching, I think the implication there is that, strict adherence to frequency referencing, maybe to DSS or some kind of standardized compound would be necessary, right?
Yeah, there's two things that needs to be taken into account: strict referencing, because we tend to use a reference positions simply because not everybody runs the same way all the time. That's the way 99% of the NMR people are, unfortunately, based upon the data that I receive. Everyone has their own pet way of collecting data. So referencing is important. But the second thing is much more important is if your standard position of the peak of a peak or a multiplet in your standard is different positionally, it is slightly different. When I say positionally, chemical shift wise is slightly shifted away from your mixture, which can happen, which invariably happens in biofluids, like cell extracts and plant extracts and things like that. We do use alignment tool. We borrow that alignment tool from NMR Pipe. NMR Pipe has a very nice alignment tool of Spectra, but instead of supplying Spectra to it, what we do is we take those regions of interest, and take all the models in that region of interest and generate a spectra out of it. So that spectra has only those peaks, nothing else. And then so it makes it much faster to do alignment. And then we use the alignment correction in our search, if you may, from the database to the unknown. So that is, one is chemical shifting properly, and another one is aligning your reference to your unknown purely that's purely because of the system that you are dealing with. That could be pH, it could be reason, could be anything under the sun, including pH, temperature, other compounds, whatever. Yeah, both are important.
Okay. Next question. This one comes from Brian Antelek. Is the processing time long?
Typically, it's an interesting question. If you had asked me about 2 years ago, I would have said 1Ds are faster than 2Ds. Now I'm going to flip and then say 2Ds are much, much faster because of your input points are much smaller than the input points in 1D. The 1Ds are typical organics, if you may, organics that I have, which is, mixtures of compounds and things like that. They are 1 to 2 seconds, 1 to 2 minutes. I wish it could be a second. 1 to 2 minutes of processing. If it were more complex things like cell extract or biofluids or food sciences, food extracts, things like that, they too take 2 to 3 minutes. Again, these are computational numbers. Because of computational numbers, it depends upon the hardware that you have. All my numbers are based upon my MacBook, which I use as my engine. And so your processor in there and how much memory you supply and what's the disk read-write speed, things like solid state versus HD. So those things are all add to your computation speed. So my numbers that I am telling you and what we actually published in our paper for each of the examples that are in there are based upon a MacBook Pro. I have an i7 quad-core MacBook Pro. My virtual machine has 4 GB of memory, and none of the rest of them are useless. It's a quad-core. So those things do matter. As far as I remember, there are people who like to put much bigger hardware into it. So there is a hardware dependency in these numbers. Just keep that in mind. 2Ds are about a minute. And if it takes more than 2 minutes, it's a very complex systems, but about a minute.
And I know from personal experience, once HD craft for high dynamic range is involved, then the processing time actually goes up because now you have to do multiple iterations of craft to do the large peaks, subtract them out, and all that. And of course, you can have as complex of a spectrum as you want, but if all you're interested in is a small, segment window, then the processing time is going to be small regardless of how complex that spectrum is. If you're trying to go for the whole entire spectrum, the computational time, of course, is going to go up.
Yeah, so you can focus on where your answer is.
Okay, next question, also from Brian. Has anyone applied craft to diffusion data? And that seems like a very natural application of craft.
Yeah, that's a good question, Brian. To be honest, when the craft was, I don't know whether Scott Bradley is in the meeting today. He was my postdoc when I was at Lilly. He probably remembers craft. The origin of craft was to apply this to DOSI. That's where we started this whole thing. Try to do Bayesian-based analysis and then use it for DOSI analysis. But that went on the side because our applications became more and more complex into some more simpler systems like fermentation broth and things like that. So the idea is certainly valid. If you want me to show you results, I don't, but I don't see why not, because that's where at that time we called it Band-Aid instead of craft. Original Band-Aid result, probably the first Band-Aid result was on a simple DOSI spectrum, trying to fit into multiple component into DOSI. That's the first one, but we never followed it up, to be honest. Yeah. Good question. I don't have an answer. I don't have an example.
And if you think about it, all DOSI and really all relaxation experiments, they're very similar to just real-time reaction monitoring, except that instead of real time, the peak amplitude changes, the next time you take a spectrum and, change some kind of delay or pulsing rate. So if it works for reaction monitoring, it seems natural that it should work, perfectly for this kind of data. I think for diffusion data and relaxation data, one place where Kraft can probably absolutely shine is for diffusion data when you're going out to long diffusion times or very large gradient strengths, and your peak amplitude is attenuated by 90 or 95% of its starting value. It's very hard, using traditional integration or peak height approaches, especially of course in crowded spectra, to measure the peak amplitude accurately. Or if you're doing something like an inversion recovery experiment, when you're near that zero crossing, it's almost impossible to get that, to accurately get that information traditionally. But I think as more people start to use Kraft in all of these applications, we're going to see some of these problems, being overcome.
Yeah, that is a very, very, very good point. And you probably see a starry night in my screen. That was deliberate because I want to share a different PowerPoint, if I may, that alludes to so I hope you can see this. So in one of the slides that Dave showed up is in the early point of a reaction, when you're doing a reaction monitoring, the early time points, the reactant, the products are not formed yet, they are very small, and you end up having difficulty and even with crafting. The same thing would be in a diffusion when it is inverting or when it is very small. You do get into these kind of trouble. But what you can do is we can do this MISTA, which I alluded to in my slide there, but I didn't talk about, but I talked about this in Ivan conference, was you can take, for example, this model, which came out of the first trace, just that model, and spike it. So this shows, what this shows is, if I take these two, this peak right here, and then this peak right here, and try to do conventional crafting beyond a certain limit, it doesn't find this particular model, the downfield one, and so it becomes all zero. But what I can do is I can take the model, not the first trace, but just the model from the first trace and add it up to all the traces in all the FIDs. I simply take this exponential decay function and add it to all FIDs. Now I know exactly what I added, and then I can do crafting or my computation. Now this peak is sticking out, and I can finish my crafting, and then the craft table, I simply say, hey, your table amplitude includes a model that I added, just subtract it out. And then you can plot it like right there. Wow. The same data, after I just add this model, do crafting and remove the model, I can do plot. It looks very similar to. So even trace analysis, there are opportunities here by simply taking your model of interest, either from the reactant, the last trace in your reactant, which is a product, and add it to everybody, and then simply subtract it out with the table, or the reactant, which is the first trace, and add it up to every trace, and then take it out in the craft table. These kind of a tabular approach allow you to manipulate your FID in some ways, your individual FIDs, just in the region of interest, not everywhere. I'm not adding all these gunks that is of absolutely no interest to me. I'm not adding to every trace. I'm just adding only just that one model that it came out of one trace. And diffusion type of thing, that's exactly, we can do the similar thing. When it becomes extremely small, you can actually you can do a model spiking. These are all in silico, remember? No experiment is being done. You're just doing it in silico. You perturb it with a model and remove that perturbation out.
Yeah, this is classical spike addition from analytical chemistry with a modern twist. This is pretty brilliant. This is something I would love to try. This is very relevant to the day-to-day that we do, since we're in the business of looking at trace process impurities.
Yeah. So this is a recent one in my wandering in the craft space. So it's not, I haven't even done anything to this. So it's not even in my UI, if you may, in my craft software. But it is an interesting way to improve quality of your result, which is nothing new. I'm not doing anything that we don't do in the frequency domain. I do the same thing.
All right, thank you. Next question. This one is from Bob Berno. Krish, this is a very interesting one. Can craft be used to process spin noise data?
In the break when Andrea was giving talk, I did see that. Bob will be able to explain what, I don't know what, when you say what spin noise is. If you can explain that.
Is it Blumich that did a lot of seminal work on that? Correct me if I'm wrong. Anybody?
I am willing to I'll listen to that, because I don't know what he means by that actually. We can talk about that if he's not still in the meeting.
Bob, do you want to comment?
Maybe he left. I took too long.
Okay. All right. Next question. This one is from Ken Sharp. Can craft process non-uniform sample data?
Yes, of course. We don't actually use. I'm sure if Frank Delaglio is in the meeting, he will be smiling at me at this question. Exactly. We don't actually do non-uniform sample data as input, which is definitely potentially possible. I don't have that tool with me. So what we actually do is we sort of make use of the conventional NUS to uniformly sampling algorithms that are around, right? Everybody has their own way of how do you fill the gaps in the non-uniformly sampled data. We use iterative soft thresholding that is in NMR pipe, and we use that to take your non-uniformly sampled interferogram and generate the uniformly sampled interferogram, and then use that quote unquote filled interferogram that into Craft Engine and take the results out of it. So fundamentally, I would like to see, if there is any computational people listening to me, I would like to see non-uniformly sampled data as input to directly Bayesian type of, or any time domain analysis there. I use Bayesian purely because I like it. It is very, very good. It is a sort of a I consider that to be a sleeping beauty, and extremely easy to use, and so I use that. But if there is somebody is willing to show me something that is better than this, I'm willing to listen. I'm sure Larry Brathwaite would also be interested to listen. But my point is, it doesn't matter what time domain analysis algorithm is. If we think in terms of, my point is, if we think in terms of time domain to tabular domain, and how we put that, non-uniform sample data should be absolutely, I see no fundamentally any reason why you cannot use that as is, as an input to fitting algorithm. This is model fitting. I don't think why it's not me, but again, I am neither qualified nor experienced to comment on that. If Frank is around, maybe Frank can explain when he's going to put this in NMR pipe.
Okay, next question is from Leela. There's two questions actually. So the first one is regarding craft protein formulation analysis. So what will be the take-home message for those who are interested in quantifying both the small molecules and the macromolecules? I mean, in principle, both should be doable.
Yes, yes, definitely, yeah.
The application to quantify proteins, especially from a 2D, that I think that would be really, really powerful. Given that craft overcomes the T1 max limitation, and the natural line width is restored, I think that's going to be, I think that's going to be a major player in actually getting accurate protein quantitations.
Okay. Yeah, I pretty much agree with you. But there is a section that I did not share. I sort of, oh, sorry, I didn't put that in there. Okay, I did not share. As you can probably say, I jumped from here. I was here, and then I clicked that add fast forward arrow right there and jumped out. But I did want to talk about this. It's in the paper as well. Is crowded spectrum, which is like protein. You do get into this trouble that Frank talked about in a couple of Ivan meetings as well. Then if your input number of points is not enough, you can't model very well. For example, I think this is an agency of first increment. Only 64 increments were collected. Actually, 32 increment. There it is. See, I don't even say, and it doesn't fit very well. So, but that's where we can play with these kind of things that is unique for time domain. For example, I can take what I would like to see is I want to take what do we do if we have something like that, then you don't have enough number of points in frequency domain. So what do we do in frequency domain? We take it, when you do an FT, you get something like this, and then we zero fill these guys, and you get much better looking. There is no operatization here, so you do see sync filters. So you can get these peak shapes much better, and then you can do in frequency domain, you can do a much better analysis. The same interferogram, it's I just zero fill it and Fourier transform. You don't have much benefit after 3 or 4 times. And these are just classic zero fill FT. So fundamentally, what is happening is this is all same dwell time, of course, the same spectral width. Fundamentally, what's happening is if you zero fill the FID, you get a spectrum oversampling. That is the same spectral width has more number of points. So what I take a gospel from one of the slides from Frank was a forward inverse Fourier transform are the same. That's FT gospel. So I asked a question of if I have a if I have a spectrum that is 64-point spectrum, which comes from the previous, which comes from the FT of this without zero fill. And what happens if I zero fill this guy? When I mean zero fill is I just simply add zeros on either side of the spectrum to take it to 1024 or 512. And what if I do an inverse Fourier transform? Here, my point per frequency in frequency domain remains the same. Because when I add twice the amount of points, then my spectral width goes up by 5 kilohertz, 4 times 10 kilohertz. So point per resolution in frequency domain remains the same. But the number of points to define the same interferogram goes up. So zero filling in spectrum does FID oversampling. And it has no value in frequency domain analysis. This is just a silly thing to do by adding zeros to your spectrum. But I can take this interferogram, which is a 32-point interferogram, do an FT, nothing else is done, zero fill the spectrum, do an inverse FT. I zero filled it by factor of 4, meaning that this is 64 point, this is 256 points. So I added whatever that 192 equally on both sides. And I did an inverse FT. I get this an interferogram that is 4 times oversampled. And this I can take and do my analysis. So I can take either I can do zero fill. This goes into picture of I don't have to even actually do zero filling. I can take 4 random traces and add them side by side, generate the IFT, and then generate all 4 of them oversample in one shot. Let's skip that part of it. But if I take that zero fill inverse Fourier transform interferogram, and I can do a Bayesian analysis, I get them all. Whereas if I just do the same interferogram, I get only one peak right there. It defines only one peak. I didn't collect anything. All I did was I did an isosphore and did craft. I essentially made this interferogram much better defined. Obviously, I can't just do it forever, but I can do it much better defined, 4 times, 8 times, better defined, oversampled, and supply that oversample data, which has a lot more number of points than this. But starting from the original fit and do this. Then if I take that HNCO, you can see that I can fill them up. I can generate a table, and I can generate, these are traces that we talked about in one of the slides. And I can do an N15 HSQC and faces. You can do the same thing. We have a small molecule and a big molecule. After the table is in your hand, you have filters called spreadsheet. You can filter, don't take anything that is sharper than this. That's my small molecule 2D. Anything wider than this, that's my protein 2D. Fundamentally, you can do that. I don't have an answer, but the point being, you can do these kind of manipulations with that. That is, the ISOs is not a manipulation of the table, it is a manipulation of your input interferogram. But I just did FT inverse zero fill inverse FT. Yes, mathematically speaking, somebody told me I can't go forever, but hey, I can do up to 4 or 8. I can get the things that I want. And here is something that where the FT is overlaid on top of the craft results. And this is a craft results with every one of the cross peaks is full amplitude is in there. These cross peaks are not traces at a single position. It is the whole volume of that cross peak. This whole volume, this is amplitude, which means 2D volume. So it is possible to do this kind of stuff. That's the one I missed because of time during this. I'm glad that somebody asked this question. Yes, there are opportunities that exist. That's why I call this a perspective. I am glad I'm hearing these kind of questions, really. I don't have an answer. I don't have an example to show you.
And Krish, actually, just to build on that, so apropos our conversation from yesterday, actually, about noise, sampling, and zero filling, right? I think we came to the conclusion that, doubling your acquisition time and doubling the actual number of points that one collects changes the way the zero filling extrapolates in the spectrum. And so given that you're zero filling the spectrum and then going back to the time domain, is there an analogous effect where, right, because the zero filling, right, you're not actually sampling those points, you're trying to extract, it's trying to linearly extrapolate all the points in between. So I mean, clearly the results speak for themselves, but are there any hidden artifacts or kind of watch outs that people should be aware of?
Yeah, that's why I do this rather than zero fill. When I first started off with, I talked about zero fill in this slide, but actually what we do is we actually take all the interferograms and then group them in random combinations of 4, right? 4 or 8, whatever, if you're trying to do ISOs 4 or ISOs 8. Take random combinations, just pick a random interferograms, and then take the FT result of that. This is just an FT of these, no zero fill, and then stitch them side by side. So the noise is, now I am actually throwing in the noise into, instead of zero filling, I'm actually noise filling, except my noise regions also has peaks. Then what I do is I simply use the trick that I use in 1D, that is a digital filter just this region, not downsample, just digital filter that region and get that back. So what is the actual answer to your question? I am very good with dancing around your questions. In this case, I don't know, but we need to look into the uncertainties of all these numbers to find out what it does. The good question, I am glad, I'm in some ways, I'm actually very glad that I am telling a lot of these questions I don't know, or I don't have a proof of concept. But the fact that we are able to generate these kind of questions mean there is an interest in this kind of a new paradigm in the way we want to analyze this data. So there are things that we can do. And in the paper, I also describe this, if you want to go back and read. Craft is not a software. Craft is a workflow. It has a workflow of known tools that we use all the time in our world, NMR world, tool we use all the time. There isn't a single tool, we don't use the Bayesian tool all the time, but we do use a lot of time domain analysis tools. but it's just another time domain analysis. We don't use it. It's a sleeping beauty. It's 1990 it was published. So we use the tools that is already available. My point is, put it together in a different way than the conventional way. That is, let's do the first FT and then do all kinds of stuff that we need to remove that effect of that FT. But pet peeve one more time is, let's write algorithms to do baseline correction. Let's write algorithms to do phase correction. The definition, even the phrase phase correction bothers the hell out of me. That's phase correction because we don't like dispersive component in our visual spectrum, because spectrum is visual, nothing more.
It's aesthetics.
It's aesthetic. There is something to correct. Phase is phase, what it is. It is the phase of that magnetization when after you pulse, sorry, or at the time you are collecting the data. What are you correcting? You are adjusting to make it purely absorptive, that's all. So that you can do other things. Pick the frequency, get the amplitude integral done properly. It's the other things that you want to do with the Fourier transform result that necessitate you to do phase correction. And we spend all our time into doing best phase correction there is.
And Krish, I know there's a few more questions, but one topic that you just brought up that I think deserves a little more exploration is, you brought up this concept of uncertainty. And I'm sure some people in the audience, especially the qNMR folks, are wondering, how does one deal with some of the uncertainty of craft, right? And I think this comes in multiple components. There's the intrinsic Bayesian uncertainty, and then there is another orthogonal uncertainty that's actually subjective because it depends on some of the user-defined parameters and segment windows and all that kind of stuff. So, and maybe even some of the digital filters that you've mentioned. Perhaps you could, comment on that.
Yeah, I mean, it is what you have to be, pretty much the table. Not the table that I show because it looks nice on a PowerPoint presentation, but the table that actually comes out of spits out of the Bayesian analysis. In my case, it's a big table. It has all the components. It has the uncertainty of each one of those computations. So we have information that we seek in the raw table that we have. So how we use that is important. But having said that, we all need to also keep in mind anything that you do to the Fed before you subject that to a Bayesian or any time domain analysis should be carefully thought out. HD craft is one example. We actually do a craft one, take those models, subtract it from the FID. There you go, you perturb the FID. Right? You take the FID and then digitally filter downsample a region. You need to keep in mind how good is your digital filter is, how well the residuals, how bad it perturbed the amplitude and phase. So in the paper that I showed up to 100 times vertical scaling and then said visually you can't see any perturbation within that window that I selected, but that is within the window that I selected. So these are the kind of, in other words, the focus in the moment you get into time domain and this craft type of analysis is the focus should be in terms of how does this answer my question within the uncertainty or within the accuracy or reproducibility that I am looking for, and try to look for reasons why it is not accurate, or have more uncertainty, rather than again I go back to frequency domain and then say rather than putting our effort to make that spectrum look better so I can extract that information out of it easier, more accurate, more. You are doing something to the spectrum as well. So here you're doing to the Fed. If you do to the Fed, but there are lots of benefits from going from Fed to table. That's what I have been trying to trying to demonstrate. And the answer to your question is, yes, all of these need to be taken into consideration. So in the qNMR package, I do write an applications package for qNMR. I try to keep these peaks in the middle of, right, every peak that you pick in that examples that I showed, every peak segment that I decide I want to quantitation of, I try to keep that segment in the middle of its own region of interest, its own digital filter downsampling window, meaning that is least perturbed by that pre-processing I'm doing before I send it to Bayesian. So that is important. You need to understand what you're doing to the FID before you give it to Bayesian, and is there a better way of doing it? MISTA is classic examples. Yes, I am adding, but I know what I am adding, but it gives me something out of there. Yeah, I'm able to improve, in fact, the probability of finding that peak just by adding a model to it, which I know what I added. Yeah, and that's the kind of, your questions are incredibly valid, and I don't have all the answers, but that's what we need to be thinking about to make it better and better and better. In fact, I mean, I want to do a shout out to Gennady. Gennady has sent me so many questions that were very, very, makes me sit up and think. And so that's the kind of questions we need to be asking. I feel that we need to go from visual tool game to number games. We can take this technology much farther if we start to think. If everybody puts there's more people who knows about these things better than I do. I'm just putting out saying that, hey, listen to this. There's a way to think about it differently. So,
I mean, I think with the whole, recent explosion of data science and, application of chemometrics, especially in the last few years, I really think that, this whole, craft paradigm is going to make NMR much more amenable to that kind of stuff. And I think there's going to be a lot of, non-NMR data science experts that are going to start trying to, apply their techniques to extract that information that, traditionally as spectroscopists, it's very challenging for us to get.
Yeah.
Do we have more time for more questions? I know there's a couple more in the chat box.
If there are in the chat box, fair game, go for it.
We have as much time as you and the audience want to stay. So yes, if there are questions in the chat box, or if there are any other questions to come from the directly.
Okay, let's finish off these chat box questions. So there was a question also from Leela about for craft carbon or 2D HSQCs, can you get useful information if methine and methylene happen to fall on top of one another? I would imagine the two FIDs would semi-cancel each other out. They would, right? If it's the same frequencies, you would. I don't think there's.
Yeah. It's a very good question. I think the fundamentally it is a question of, is my cross peak, but how you analyze the cross peak, how you get the information of the cross peak is the second step. The first step is my cross peak resolved in either F2 or F1 in order for my collected data resolve it. In order for my collected data, meaning the T1 max or acquisition time, resolve it, right? That's important. It's not going to do a magic, but if it is right on top of each other on both F1 and F2, I'm not talking about how it looks like in the spectrum, because when you generate the spectrum, you do apodization, you zero fill and broaden the thing out. So if it is the frequency is resolved in F1 and F2, F1 or F2, not necessarily both. I make that point in the paper as well. If it is, then yes, craft will actually pull that apart quite nicely. The additional advantage you do have in craft, it's not just about frequency being overlapped fundamentally speaking, if you have an overlap, meaning the frequencies happens to be exactly the same, but one is broader than the other. One is broader than the other. Decay rate constant, it will pick it out of the decay rate constant. So it will separate it out. You may have in the frequency column, you may have the same frequency, but in the decay rate column, they have two different, because it says I can fit this only with, not with a single exponential model, but two exponential model. One is fast decaying, another one is slow decaying. So yes, so you have yet another tool, and the phase, of course, tool that can separate it out. So the probability of two peaks, one positive and one negative, I'm not going to talk about it as CS and CH2, because then we need to think about, perhaps you have a coupling that will actually not overlap these two. So anything that would pull them apart is good enough. Anything, frequency, decay rate, amplitude, of course not. That's a negative, canceled out. That's exactly your point, canceled out. Whereas amplitude and phase or decay rate, if it can fit only with those, it will fit. I have had examples like that a lot of times in the 1D. You have a broad resonance, right on top of it is a frequency. Actually, after the Bayesian, if you go into that frequency difference is within the 1 over the acquisition time at all, but you can separate it off. So yes, it is potentially possible. In fact, if there are examples like that, that will be interesting challenge to show Kraft can actually do it better. In time, I'm not saying Kraft, I want to apologize. Kraft also happens to be the software package that is commercially available. I'm not talking about the Kraft package that's commercially available, because that becomes marketing. I'm talking about Kraft as a technique that is potentially possible, that it will pull apart those by doing it in Kraft. The thing which we don't keep in mind is in 2D, what we are looking for is resolution in either this or that. That's what a 2D was many years ago. What did we do? Why did we do 2D? Separate the frequencies in two different dimensions. Correlation is one more. That's a different story. Yes, we wanted to correlate a coupled system, but it separated out from two different frequencies. We did this in HSQC, carbon, proton. I have a more overlapped proton. I want to resolve it in carbon. Keep that always in mind. As long as it is resolved in one or the other, Kraft will do a fantastic job. But if it's on top of each other at the same time, on the same place in both dimensions and the same decay rate constants, yep, that's, as far as Kraft is concerned, that's isogamous.
There's actually I want to skip to the latest question by Vladimir. It's actually a really good question, because this is something that we've actually dealt with. What about imperfect shimming?
Very good. Okay, so two answers to that. Number one is because as we have implemented it, or we have used it, we use pure exponential decay. Obviously, imperfect shimming means that's not pure exponential decay. So what we did in the very early stages of Kraft definition was, that's why we defined the segment. So a poorly shimmed singlet, I actually have examples that it'll take me longer to find that slide to show you, but so I'm going to explain. A poorly shimmed signal, or you have another shoulder to your peak, your singlet, because we don't define that as a singlet when we have the Bayesian when Bayesian is analyzing it. We simply say, here is a fit this to as many do as many iterative processes as you want to, until there is no probability of finding a peak. So what it will typically do is it will fit that resonance, which is this poorly shimmed with a leg resonance. I define that as a resonance, into multiple models. So a segment should define the resonance. Then all the models that defines that resonance are within that segment. And so it will add it together and give you an amplitude that belongs to that poorly shimmed resonance. But the problem is, if I take my Z3 or Z4 in the shim, yank it to one end, will you be able to do that? That's as bad as you are pulling. Your segment window need to go wider and wider and wider in order to accommodate all the models that are needed, all the exponential decay models that are needed to define that poorly shimmed wacko line shape signal. What that means, you just lost your resolution even in the craft domain. So you lose a resolution when you don't shim. And from a craft paradigm, that's what that is. You need to expand your segment width wide enough to cover all these imperfections, if you may, into that. Alternatively, the second answer is we have done this lately as well. Use tools that are available, like Fiddle is one of the most very powerful tool that is available, which will do fit deconvolution. Fiddle that was published many years ago by Gareth Morris's group. And you can take one of the peaks in your one of the peak, meaning a singular peak in your system, like a DSS or TMS, and do a spectral reference deconvolution, and take the resultant FID as the input to your graph. And so you sort of did a post acquisition reference deconvolution, but that is not unique for craft. It is for, that was used significantly very well in DOSI, in how to do DOSI analysis. So yes, if you have poor shim, your segments need to be wider. How wide? It depends upon how poorly shimmed you are. And the segments are wider, the more and more wider it becomes, you won't be able to separate a resonance that is close, a real resonance that is close by. What did happen? You lost resolution. And that's true even in here.
Okay. And I think one last question, actually 2 questions. Does craft 2D processing avoid problems such as T1 noise?
Good question. I used to have this argument with somebody else in the past.
Noise.
Let's not talk about who that is. But an interferogram, a T1 noise is nothing but the uncertainty in every one of those points in the 64 points that we collected. Uncertainty meaning that it's not where they are supposed to be in a perfectly fitting sinusoid. And that where they don't fit, why they don't fit is your experiment or whatever we call T1 noise. It's the Fourier transform of that gives you spread across your entire parallel to F1. But that's an uncertainty. Your input has an uncertainty that will be reflected in the uncertainty column of your amplitude, frequency, decay rate, or phase. So that uncertainty will be wider. So you may have a cross, when it is converting all the stables into cross peaks, you may have 2 cross peaks that are close to each other. May turn out, it may say that's a single cross peak because it is uncertain because of your T1 noise. That's not really across the entire spectrum. It's really noise in the uncertainty of your digital points in your interferogram. That uncertainty will add to this fingerprint table that I was showing you. So 2 very closely spaced, both in F1 and F2, may merge together. So you don't get any uncertainty. Any T1 noise, somebody actually commented so a long time back when I showed craft 2D spectrum is, oh, you don't have any T1 noise. Of course I don't have any T1 noise. There's nothing called a T1 noise. It is uncertainty in your number. And that number is what it is. The Fourier transform of that is what gives you T1 noise. But if I'm not doing Fourier transform, I'm just having the uncertainty, I have that uncertainty column which dictate how this cross peak is supposed to be. So I'm simulating only the center of that uncertain window, and then I say that uncertainty increases your fingerprinting table, and so there's no T1 noise per se. That is an artifact of Fourier transform of a poorly digitized sinusoid. Poorly digitized meaning the amplitude of that sinusoid at every point is not where they are supposed to be. For whatever reason, it can be experimental reason, it can be your instrumental reason. I don't know, but whatever that is, that's all you are collecting anyway. But you're not collecting anything beyond that, and that's 64 points. What gives you the noise? Fourier transform of that.
And then one final question relating to fast relaxing species. Let's see, where is it? So somebody asked the question about whole plant cell wall extracts and lignin. So, you know, trying to figure out the ramification. I guess the question is about, you know, craft and modeling the decay rate of polymers and slow relaxing species, if you want to comment on that.
Yeah, it is a very interesting topic. We have been working with some polymers lately as well. ISOs can be a very useful trick, whether you do it, ISOs meaning oversampling, could be a very useful trick to define these broad resonances, meaning fast decaying signals in time domain. Even if you don't collect it, if there is a way we can do in silico oversampling in one, it could be. So I just said it's a miles to go, as is number 6 in this. It's a very good question. Again, I do have some preliminary examples of that. I haven't spoken with my collaborator and got permission to show you that, but it's very promising. That's in the polymer area. I don't know about the, you know, when you said plant extract. So if it's polymer, we think that there is a potential opportunity exists. As long as we keep in mind, we are also fighting the distribution of chemical shift for a resonance, just like in improper shimming. Yeah, you have a distribution of chemical shift due to local changes, and we need to keep that in mind. But those are all post. These are all interpretation. Yeah, that interpretation comes later after you have the table, and how do you mine the table? Then you have to start thinking about, should I just take one line or should I take multiple lines? Because I am a polymer, I have distribution of chemical shift, so I have to look at it from a band point of view. Should I take all the models from the band? So those are all chemistry-driven questions as you mine the data. And the data is coming from your FED. I am hoping the ISOs trick on the 1D, which this gives a very fantastic advantage, because you can have broad resonances and sharp resonances in your spectrum, and you can now get rid of the sharp resonances using the CAS method I talked about, and take the broad resonances resultant FID, which is unnecessarily long in acquisition time because the signals decayed out by then. Then I take only the first 1/8 of that and then do an ISOs 8. So I got the same number of points, but oversampled by 8 rather than over acquired by 8, just for the broad resonances, simply because from the table I was able to remove those numbers out, those resonances out of the original phase. So there are lots of games one can play. Polymers is definitely a good example. We do have some preliminary results that looks very promising.
Okay, I think that covers all the questions from the chat box. Perhaps we could open this up to the audience if anybody wants to unmute themselves.
John?
Thanks. He just answered my question, so fantastic. I might want to get back to him again. But hi, Krish, that was freaking awesome. I'm just blown away by this. Honestly,
thank you.
I'm slightly out of my depth here, but this is. I'm trying to retire in a little while. I think I can't now. This is too exciting.
I don't want you to, John.
It's so good to see you. All right, sorry about that.
So are there any more questions? And, oh, Okay, and it looks like there's a thanks coming in here from the chat. And so actually then, if there are no more questions, I'd like to thank Krish and our panelists today for a world's record roundtable workshop that stayed interesting straight to the end. So thanks very much, everyone. John could not stay for the whole thing. He actually had another appointment. And so I will thank everyone for John as well. So with that, let's close up the meeting.
Thank you. Thank you.
Okay, I'll bang the gavel.
Okay.
Brilliant. Thanks.
Bye.
Bye, everyone. Thank you.
Bye, everyone.
Bye.